Okay, so we'll look at some homework here. Um, First we'll look at an old one, that gauge problem, converting a pressure gauge into a volume gauge for a tank is what we'll look at here. And that's a pressure type problem here, I think. I think it's in here somewhere. That looks like it. Okay. So what we got here is we want to take this pressure gauge. We want to take these pressure gauge readings and turn them into basically a volume gauge for this tank is what we'd like to do. So we'll have a look at that. If I can get there from here. All right, let's force. Okay, so what we want to do is just use the same gauge, but turn it into a volume gauge for the tank. Now, what you need to do first is kind of get a deal going here where you can find volumes. So what I would do on this thing first is I would get the area of the tank, and that's 3.86 feet by 3 feet. Okay, and this will get the area, is what it'll get. So when you just multiply those together, you'll get the area, and that is 11.58. So that's the cross-sectional area of the tank, and that's square feet, and that's the area. All right, now what we want to do next is figure out the volume. Now you'll notice here on the gauge that it shows 0, 2, 4, 6, and 8. So let's just look at what happens when we've got 2 psi, okay? When we've got a reading of 2 psi, what we know is there's 2.31 feet of water per psi. So what that means is we've got 4.62 feet of water. So when that gauge reads 2, it means there's 4.62 feet of water. All right, so if you want the volume in the tank, what you do here is you take the area, cross-sectional area, 11.58 square feet, and then you multiply that by the depth, okay? So area times depth will get you volume, and that would get you the volume in cubic feet for 2 psi, and that comes out to be 53.5. So that's the number of cubic feet of water for 2 psi. Now we want gallons, so I take the 53.5 cubic feet, and then there's 7.48 gallons in a cubic foot. Okay, so if you multiply that through, you'll get the gallons. And what you get out of that then is you get 400 gallons. So when that gauge reads 2 psi, what you've got in there is 400 gallons. And from there you can just proportion things up, because you've got 4 psi is twice 2 psi. 6 psi is 3 times 2 psi. And 8 is 4 times 2 psi. So you can just do it like that. It's all proportional. So you get 800, 1200, and 1600. So that's what you're going to do with the gauge, okay? So that's how that would go. If you look at a modern readout on a computer screen, that's how it's done. They use a pressure transducer, sends a signal that tells what the depth is, and from there the volume can be calculated. is that okay? You got any questions for that?
No, that was great, actually.
Okay, good deal.
I knew I missed a step in mine somewhere, but you got that much, like, stuff on scratch paper,
Yeah.
kind of hard to tell where.
Yeah, right. I mean, I know what you mean. All right. All right. So there we go. So let's have a look at some of these other ones then, if you'd like, in chapter 8. So this is the stuff that's due on Monday. There we go. So calculate the force at the bottom of a 12-inch diameter well, which contains 125 feet of water. Y'all okay with that? I would just find the volume of that, and then based on the volume, find the weight. Keep in mind that the weight is the force. You know, so if you got this kind of thing, I usually just find the volume, which, you know, you can run through the numbers on that. Watch your units on the volume. It should be 98.2 cubic feet. And then find the force, which equals the weight. And that comes out to be about, you know, you might get some rounding differences there, but 6,126 pounds, something like that. Okay. So that's just a kind of a check halfway through as you can find the volume. Are we okay with that? Any questions? Good. All right. Okay. Now the next one here, we've got a dam that's basically got 22 feet of water on it. The dam is very long, 170 feet. So what you want to do is find the area of the water. So one thing I point out on this is the 28 feet doesn't make any difference at all. The height of the wall of the dam doesn't matter. It's the height of the water. That's what creates the pressure. Okay, so use the water height. And so you're going to want to get the area. Now, before you get the area here, you're going to want to anticipate that you're going to use PSI, pounds per square inch. Okay, so you're going to want to get these into inches. All right, so for instance, this is 2,040 inches. Okay, and you'll want to get that 22 feet put into inches also. And then you'll want to find the area of the dam in square inches, and that should come out to be 538, 560. So that's how many square inches are in the dam. Now what you'd want to do next there is find the pressure. Now remember, what you want here is the average pressure. So you're going to have to pull down there, and the average pressure occurs halfway down. So that depth there will be 11 feet. Okay? So you want to find the pressure 11 feet down. And finding pressure, remember, don't make it complicated. It's just the depth times that constant is how you get it. There's nothing more to it than that. So don't make it harder than it is. All right. And then what you're going to do next is you'll find the force. And what the force is the pressure times the area. And you can run the numbers on that, and you should get a pretty big number. So 2,565,161 pounds. When I calculated it out, that's what came out of my calculator. Again, if you round, you might get something a little different. You know, taking that out to the nearest pound, it's not like it really needs to be done. Okay. So any questions on that? Yeah.
If it's 22 feet high, why you, because you subtract that from 28, so.
So what I'm doing, I'm taking half of the 22 to get 11.
Okay.
So, you know, so first off, I'm not using the 28 at all. That's got nothing to do with anything.
Right. You get type of water.
Right. I want the average pressure. So to get the average pressure pushing on the dam, I take the pressure halfway down the 22 feet. Is that good? So half of 22 is 11. Okay. Okay. Okay, these next two are kind of similar here. What you want to do is you want to find, you're using this basic relationship here where you're going to find the force is the pressure times the area, okay? So what you want to do is find those things. Now the pressure is in PSI. Now what PSI is pounds per square inch. Per means a fraction, something that goes underneath a fraction line. So being as you're doing pounds per square inch, your area you're going to want in square inches. And then that pressure should be the average pressure. Okay. So when I'm working through these, I just want to find the average pressure, which is at the average depth. And I also want to find the area in square inches. So for instance, on this one here, I got 24 inches for 2 feet and 24 inches. Okay. So 2 feet by 2 feet is 24 inches by 24 inches. That's going to get me an area in square inches, which is what I want. Okay. And then I'm going to want the average depth on that. And the average depth is to the middle, which is 6 feet plus 1 foot more. Okay, so that'll be 7 feet to the middle. That's where the average depth is at. Okay. So we good with that? Any questions on that so far? And then you just want to go ahead and find the pressure. It's 3.03. And then you want to find the area, which is 576. Okay. Now this 20-foot high tank, that's a 16-inch valve, which means it has a radius of 8 inches, which means the area is 201 inches squared. And then the pressure on that one is 8.05. Pounds per square inch. Okay. So that's how that one works. So we're doing okay with that? Okay. So that next one, 8.5, a blind flange is just something like that. It's just so it's right there about knee level for that fellow working on that stuff. It's just like a T or a pipe that just dead ends, and then you put a plate on it, you bolt it on. Okay. So, yeah, plug, whatever you want to call it, right? It'd be just like, a closed gate valve would act a lot like a blind flange. Okay. So what you get all this pressure building up, So that's why they're usually, when you see these things, they got lots of bolts on them and pretty big diameter bolts. And the reason is it's the pressure and the force. Okay, so on this problem here, this next one, what you want to do is, it's pretty straight up. You got a pressure, you can find the area, just run the numbers. I mean, that's really about all there is to that one. That one's almost too easy, you know. It's just pressure times area. That's all you got to do. Got any questions on that? Okay. How about the next one there? Got questions on this one? What I'd want to do on this is calculate those areas first. I don't know why I just do that, because it seems once I got them, everything else goes pretty straightforward. Okay. So this is like a hydraulic jack kind of thing. So what you're going to do here is find the pressure, which is force over area. And that'll be on the 1/2 inch side that you do that. So you'll find out that the pressure in there is 3.18 pounds per inch squared. Okay. And then, and I'm sorry, that's not on the 1/2 inch side, that's on the 4 inch side, because that's what you know on that one is what you need to actuate this thing. So what you need on the 1/2 inch side then is you got to know how hard to push. So what you're going to do, you're going to take force is pressure times area, and that's where you'll get the 0.625 pounds. Okay. So what you can do here, you can take a very small force, 0.625 pounds, and turn it into 40 pounds of push. But the price you'll pay for that is how far you have to push the piston. So if you want the, you know, that 40-pound force to move an inch, I think you're going to have to push that piston. It's quite a bit. It's more than 40. It's 40 divided by 0.625, which is 5/8, right? So it's 64 inches, I think. So yeah, you know, that's the price you pay for extra force, is you've got to generate a lot of extra distance. Now you could do this kind of, the quick way would be to take 40 pounds. You know, so if you wanted to do it kind of the fast way, you could just take 40 pounds and then take the ratio of either the diameters or the radii, whichever one you want, squared, okay? So 0.5, which is 1/2 inch, over 4 squared. You could do it that way. You got to remember to square it. And that would get you the answer pretty readily too, okay? So that's the shortcut. That formula isn't written down anywhere though, so it's kind of on you to remember it if that's what you want to do. Questions on that? Okay. All right. The next one there we've got is this gate, 4x4 by an inch thick underwater. The gate weighs 220.5, so the gate's got that going on. We want to find the buoyancy, and then figure out the difference in the two forces. Okay. Now a 1/2 inch there is it's a 1 inch thick. That's a 1/12 of a foot, right? So you want to find the volume of that gate. Okay. And when you do that, you should get 1.33 cubic feet. And so the buoyancy is 62.4 pounds per cubic foot. times the 1.33 cubic feet, okay? Something like that. Okay. And that'll get you the buoyancy, and that's 83.2. So you've just found the buoyancy is 83.2, and then you just have to take the difference basically. So 220.5 minus 83.2, that'll get you the net weight or net force on that thing. And that's going to be, whatever it is, 137 pounds. So that thing will still sink in water if it's allowed to. The weight is greater than the buoyancy force. Okay. Okay, this next one here, we just have that formula that F is what, 2PA sine of theta over 2. So what you want is the pressure is taken to be 1.5 times the 85 psi, okay? Because you want to be safe in your design. When you have water hammer and things, the pressure will go up above that internal pressure by 1.5 times. The area is 50.27 square inches. And theta over 2 is half of 90, it's 45. So when you run the numbers there, you'll get that force. So the force there is 9,063 pounds. Okay, that's how much force is going to be pushing that way. So what you need then is the soil to be able to push back to hold that block in place. Okay. So you want to know what the area is so that the soil can push back to counteract the 9,063. So the area then will be the 9,063 pounds over how strong the soil is. So every square foot of soil can take 3,000 pounds. Okay. So what you're going to get there for that required area of the thrust block is just a little bit more than 3 square feet. So that's how big to build that thrust block on the soil side where it contacts the soil. Everybody okay with that? Good. Okay, this last one here, we've got this block in the water, and we want to know how deep it will sit in the water if it floats. Okay. Are there any questions on this one to start with? I guess the key to understanding this thing is, you know, the weight of the thing is 322 pounds, right? Now, if it's going to float, What's the buoyancy force going to be for floating? It's partially it's specific gravity. I'm looking for a number, like how many pounds up will the buoyancy force be if that thing's going to float? Probably right at 322, right?
Well, the top is of the water.
Good point.
If they were exactly equal, it would be stagnant in the water.
Yeah. Well, let's see. It could be stagnant in the water. It could be stagnant in the water if it was floating like this, though, right? It would just be doing what it's doing. So what you want to do is figure out when it's balanced, when the force up equals the force down. That's when it stops going up or down. When it's in equilibrium, it's kind of the fancy word for that. Okay. So what you want to do is figure out when that buoyancy force balances the weight. Okay. That's when it floats. So if you take a cork and throw it in the water, most of the cork will be out of the water, right? Because the cork's very light, it doesn't need much buoyancy force to hold it up. But if you take a heavy, a more dense wood like oak or something and throw it in the water, it'll sink a lot deeper, right? Because it's heavier, it needs more buoyancy force holding it up. Okay. So what you want to do here is figure out when the buoyancy force equals the weight. So what you're after here is 322 pounds of buoyancy force. That's when it balances out. Y'all okay with that? Any questions on that bit there? So what you got to do is figure out how much of it needs to be submerged to get you the 322 pounds of buoyancy force to balance it out.
How much needs to be submerged to get that 322 pounds?
Right. Yeah. And there's different ways to figure this thing out, but that's the basics of it. The downward weight has to be balanced by the force of buoyancy up. If they equal each other, then it just stays put. It doesn't go anywhere. It's just sitting there then, which is what floating is, essentially just sitting there. Okay?
Rock needs to be submerged to produce 320 pounds of buoyancy or pressure.
I'm sorry?
Buoyancy is a pressure, right?
Force is not a pressure, no. Force is pressure times area.
No, I'm talking about the buoyancy, like.
Buoyancy is a force. I mean,
Yeah.
you kind of think of it as a pressure differential in a way. I don't know, it's hard to.
Define it.
Yeah, I mean, well, there's different ways to define it. Really might be a more accurate way to say it.
Yeah.
I think in this instance, I'd look at buoyancy as more of a force. And look how it's calculated, and then from there back into how much of that board needs to be submerged.
Mm.
Okay. So I'll let you kind of kick that around if you need to, but that's a bit of a hint on that one, okay? So just look at what it takes to get a buoyancy force of 322 pounds. Okay. Other questions on that? All right, so we'll call it good.